Why is blood red and not blue? Chapter 1. The Red Answer. If you prick a finger and watch the bead rise, it brightens as if the body had learned a trick from the sun. That small dome glows red, no hesitation, no moodiness, as though it had always been waiting for the world to ask why. The why is both humble and astonishing. It's chemistry, yes, but it is also evolution's taste in metals, physics' opinion about light, and a story about how life moved from oceans to breath and from breath to thought. Why is blood red and not blue? Because iron speaks to oxygen in a dialect of electrons that happens to paint our lives in crimson. Begin with what you can't see. In every microliter of your blood, there are millions of cells built, like tiny lifeboats, biconcave discs, whose shape increases their surface area, so gas can trade across their membranes with the speed of rumor. Packed inside those cells is a protein called hemoglobin, crowded so tightly it is almost a crystal. Hemoglobin is an orchestra of 4 subunits, each holding a heme group, an intricate ring of carbon and nitrogen called a porphyrin, with a single iron ion anchored in the center like a pin through a brooch. That iron, mostly in the +2 oxidation state under healthy conditions, can bind oxygen. It does so with a cooperative flourish. When one heme binds an oxygen molecule, the protein subtly shifts, making it easier for the next one to bind, and so on. This cleverness keeps you alive on mountains and in sleep, but oxygen binding is only half the plot. The color our red is written in the way heme and iron handle light. White daylight is a bandolier of wavelengths. Some wavelengths, when they strike a material, are absorbed, promoted into electronic excitations like brief, invisible fireworks at the molecular scale. Others bounce or pass through. What you see is what survives that molecular gauntlet. In heme, the porphyrin ring is a system of conjugated electrons spread out, delocalized, able to dance when light hits. There is a particularly strong absorbance feature called the Soret band, soaking up light around the violet-blue region. There are also weaker Q bands, with oxyhemoglobin preferentially absorbing greens and some yellows. What stays reflected or transmitted once the blue and green are sipped away is light on the red end, to your eye, to the lens and retina. The remainder is a confident scarlet. That's why oxygenated blood in a thin film, the bead on a fingertip, the arterial spray in a medical textbook looks bright red. Deoxygenated blood is not blue. It is a deeper, brickish red. Deoxyhemoglobin changes the electronic environment of the iron and heme, slightly altering which wavelengths are absorbed. The Soret band shifts. The balance of greens and yellows absorbed changes. The result is a red that broods rather than blazes. In your veins, where blood has unloaded some of its oxygen and is making its quiet way back to the lungs, it appears darker, but still red. So why do veins look blue, scribed beneath skin like rivers on a map? The answer is another argument with light, this time between tissue and optics. Skin scatters shorter wavelengths more efficiently. Red light penetrates deeper. When light dives into the skin and meets a vein several millimeters down, much of the red component is absorbed by hemoglobin in the blood. The blue light, scattered back toward the surface from shallower depths, escapes to your eye more readily. You don't see the blood. You see the skin's filtering. A vein near the surface can look blue, even though its contents are as red as a garnet in shadow. Press on that vein long enough to push blood elsewhere, and the blue fades. Change the lighting, and it changes again. The color is an optical illusion scripted by biology but directed by physics. That resolves a common misconception, but it doesn't explain why life chose iron in the first place. Why not copper? Like in the oceanic aristocrats, octopuses, and horseshoe crabs, whose oxygen-carrying protein hemocyanin really does run blue when oxygenated. Why not the green pigments of certain worm hemoglobins, or the violets of hemerythrin? The short truth is that evolution is a tinkerer, not an engineer. It works with what is at hand. In ancient seas, iron was abundant, especially before oxygen surged in Earth's atmosphere and ocean chemistry changed. Iron's redox properties, the ease with which it can give and take electrons, make it superb for reversible oxygen binding, provided you keep it in the right chemical environment and prevent it from catalyzing harmful reactions elsewhere. Hemoglobin's heme cage is that environment. It holds iron in a state where oxygen can bind and then be coaxed away at the tissues. The protein's architecture, its globin chains, tunes the iron's appetite. It ensures that oxygen doesn't latch on too greedily. You need to release it in capillaries, and not so weakly that it slips away before it is needed. This partnership, iron married to porphyrin, porphyrin wrapped in protein, is a solution that life arrived at, then polished across millions of years, like a story told again and again until it fits the mouth. You can hear that story's rhythm anytime your heart drums. Oxygen binds in the lungs, where oxygen partial pressure is high. Carried by arterial blood, it is released in the tissues, where the environment lower oxygen, partial pressure, higher carbon dioxide, a slightly more acidic pH, and warmer temperatures nudges hemoglobin to let go. This sensitivity is the Bohr effect, a piece of biochemical choreography that matches supply to demand without committees or alarms. Microscopic conditions change the protein's shape. Shape changes function. Function changes color. With each release, blood darkens by a whisper, a subtle shift you would not see unless you spread the blood thin on glass. Color is physics, but it is also context. Put blood in a thick, lightless pool and it is almost black. Spin it down in a lab tube, and you can watch gravity sort the layers. A red cake of cells at the bottom, a straw yellow plasma above, stained by proteins and bilirubin, the breakdown product of heme on its way to becoming the browns of feces and the yellows of urine. Even in death and recycling, blood is telling the truth about its pigments. When oxygen is scarce and skin picks up a bluish tinge cyanosis, it is not because the blood turned blue. It is the way deoxygenated hemoglobin's color alters the combined optics of skin and tissue. When carbon monoxide binds to hemoglobin, blocking oxygen, it forms carboxyhemoglobin that can look cherry red, a treacherous brightness in a suffocating body. In rare conditions, like methemoglobinemia, iron shifts to the +3 state and hemoglobin can turn chocolate brown, depriving tissues of oxygen despite air in the lungs. There is even the grim curiosity of sulfhemoglobinemia, which can tint blood green. Human blood, under most conditions, holds stubbornly to its spectrum of reds, but it can be persuaded by chemistry or poison to step sideways on the color wheel. Walk further into the story and you meet the alternatives, each a proof that red is not destiny but solution. In some crustaceans and mollusks, hemocyanin calls on copper. When oxygen binds, the copper ions bridge an O2 molecule, shifting from Q- to Q² mice, and absorbing light so that the complex appears blue. The protein floats free in plasma rather than hiding inside cells. The animal's metabolism runs cooler. Their ocean homes present different demands. Elsewhere, marine worms may carry chlorocruorin, a green cousin to hemoglobin with a slightly different porphyrin ring. Certain invertebrates employ hemerythrin, which binds oxygen directly to iron without a heme, producing a violet hue. Antarctic icefish took a more radical route. They dispensed with hemoglobin altogether in their frigid, oxygen-rich seas, running clear blood in wide vessels while their hearts work furiously to maintain flow. Life tinkers. The palate widens. But in terrestrial vertebrates, iron-bound heme inside red cells won the evolutionary audition, an answer tuned to warm bodies, high metabolic demand, and the tyranny of gravity. Humans are a footnote in the mineral history of blood. Iron has been cycling through rocks and oceans for billions of years. Porphyrins appear even in chlorophyll, the green pigment plants use to fix sunlight, where magnesium sits in the ring's middle and sends green back to the sky. Swap the central metal and you swing the color. The difference between leaf and lifeblood, between green and red, is a metal's preference and a protein's fold. It feels miraculous only because we live inside it. Red is also narrative. Cultures made myths out of Venus blue, calling nobles blue-blooded, a phrase with roots in places where pale skin made subcutaneous veins stand out. The irony is gentle. Aristocracy proclaimed itself otherworldly on the strength of optics, while the chemistry beneath skin remained democratic, all red. Soldiers have bled on snow. Mothers have watched for the color of the first smear after birth. Artists have pressed natural pigments, some derived from iron oxides, the rusts of the world, into paint that resembles the inside of the wrist. Our metaphors are saturated with blood because the sight of it is both warning and proof. It means we are breakable. It also means we are alive. Yet the question, why red and not blue, isn't satisfied with poetry. It wants the details, the small gears. So return to heme's heart. The iron sits slightly out of the porphyrin plane when deoxygenated. The moment oxygen binds, iron is pulled into the plane, flattening the ring and tugging on the protein. That tug propagates through the hemoglobin molecule, making the other heme sites more likely to bind oxygen. It's a physical change you could measure with X-ray crystallography. That geometric shift influences electronic transitions, the energy differences that determine which photons are absorbed. To make a pigment is to set a stage for light to fall, to prearrange what light will be eaten and what will be freed. This dance happens in each of your 25 trillion red cells, give or take, which live for about 120 days and then retire to the spleen and liver, where the heme is disassembled, iron salvaged, porphyrin opened and processed into biliverdin, green, then bilirubin, yellow. If the bilirubin pathway falters, skin yellows, jaundice, another reminder that color is not coat, but consequence. Even the bruise on your shin tells a chronology in hues. At first red-purple with hemoglobin, then green with biliverdin, then yellow with bilirubin as the body clears the mess. To bleed is to paint time. If color is consequence, then the final step is to see how consequence became choice in our lineage. Think of the trade-offs the body negotiates. Free iron is dangerous. It catalyzes reactions that create harmful free radicals. So the body cages it inside heme and inside protein and ferries extra iron with chaperones like transferrin and stores it in ferritin. The red cell itself removes hemoglobin from plasma's traffic, preventing viscosity from rising too high and protecting other tissues from iron's mischief. The red cell is a mature cell with no nucleus or mitochondria. It devotes itself entirely to carriage, deforming through capillaries narrower than itself, then springing back. The iron in each heme carries oxygen with a pragmatic romance. Every minute, a quarter of your red cells are streaming through the pulmonary capillaries, turning brighter in a thin pink film across a membrane as thin as imagination. The brilliance of the solution is not its uniqueness, but its ubiquity. Across mammals and birds, across frogs and lizards, blood wears the same red for the same reason. At altitude, species tweak their hemoglobin to bind oxygen a touch more tightly. In fetuses, a different hemoglobin, with gamma chains instead of beta, binds oxygen more eagerly to draw it from maternal blood across the placenta. At the extremes of sport or survival, the body adjusts red blood cell numbers and hemoglobin concentration. Highland peoples inherit variants that balance oxygen delivery with blood thickness. These are variations on a theme. The theme is crimson. Now, imagine a world where it were otherwise, where human blood had evolved with copper and the veins truly brimmed with cerulean. The culture would be different. Metaphors of calm and sky woven into fevers and wounds. Painters reaching for ultramarine to show hurt, but the physics would be the same. Light in, pigments choosing, color out. We inhabit the version life wrote for this planet at this chemistry, and it has written it red. If you hold a thin vial of arterial blood up to the light and look sideways, you will see a near translucent clarity along the edges, as if the red is a thickness rather than a property. Tilt it, and the meniscus flashes. Color, even here, is a relationship between photons and molecules, between what is absorbed and what escapes. Sometimes people think of red as a warning in nature, the blush of toxicity in berries, the flag of a wound. But blood's red is not a warning designed for our eyes. It is an accident made meaningful. We react to it because evolution also taught us to keep our blood inside. So, why is blood red and not blue? Because iron, bound into heme, absorbs the blues and greens and lets the long wavelengths pass. Because oxygen's handshake with iron flattens a ring and retunes a spectrum. Because evolution found a way to cart oxygen around warm-blooded bodies without burning everything down. Because skin and light conspire to trick us into seeing blue where there is none, while the truth beneath continues to run red. Because red is the color left over when life solves the problem of breathing with iron. On an ordinary morning, you hardly notice the color. You cut an apple, you walk, you answer a message. The heart keeps time. The blood does its rounds. Little crimson couriers bearing oxygen to the places that dream, and the places that lift, and the places that remember. You might only notice red when you open your finger on a sharp edge, or when you watch a sunrise and feel something in your chest echo it. Then, for an instant, all the explanations pull into a single point. Physics and chemistry and evolution translated into one drop that insists on being seen. This is the answer in ordinary language. We are red because of a metal, a ring, a bond, and the way light keeps secrets. It is also the answer in extraordinary language, which is to say, the same. Iron, heme, oxygen, light. And in that litany is the fact that your thinking right now is paid for by millions upon millions of hemoglobins binding and releasing oxygen, red brightening and red dimming, a tide washing through your brain. Your thoughts are red in their way. The next time you press a wrist to a window and marvel that the vein looks blue, remember that you are looking not at blood but at skin's argument with light. The blood just goes on. Red as responsibility, red as a promise, red as the quiet, ceaseless work of being alive. Chapter 2. The Blue Myth, the Crimson Truth. Think of this chapter as a guided walk museum, market, laboratory, memory palace, every room circling the same centerpiece, a pigment that looks ordinary until light strikes it and an epoch unfurls. We begin with a painting, round a corner into a physiology lab, pause under mountain air, ride a tide pool past an octopus, then return to your wrist, where a pulse jumps like a quiet metronome beneath the skin. The question is still the same one flipping its coin in your mind. Why is blood red and not blue? The answer didn't finish in chemistry. It spread out into all the ways we measure, mistake, cure, adapt, and tell stories about that red. A gallery of red. There is a reason red is the color of warning signs and ripe fruit, of celebration and grief. In a studio light, a pot of iron oxide pigment hematite, ground to fine dust, looks almost identical to dried blood. The lineage is literal. Those earthy reds that early humans blew across cave walls were weathered iron minerals, rusts born of ancient oxygen. In that ochre is an echo of heme. It is no coincidence that we trust red to carry meaning. Iron's electron rituals have been painting the planet long before our language learned to say color. But color is not a thing. It's a negotiation. When you look at blood, what you see is not what blood is, but what light is allowed to leave blood and reach your eye. Pigments write rules, heme tells light. If you are violet or blue, I will keep you. Promote your energy into my electron cloud. If you are a certain green or yellow, I will likely keep you too. If you are red long, lingering wavelengths you may pass. Blood is red because heme is a thief with a preference. That preference is adjustable. Add oxygen, and iron's fit in the porphyrin plane changes. The protein's fold shifts. The places where light is absorbed retune. The red brightens. Take oxygen away, and the red deepens. Heat the blood a little, acidify it, flood it with carbon dioxide, and the color nudges again as hemoglobin changes its willingness to let oxygen go. This is not a showy change like a traffic light. It's a gradual shading that carries a body's weather. The blue myth, explained carefully. Your veins are not blue. Your blood is never sky-colored. It is crimson all the way down. And yet, veins will stare up from pale skin as though inked in cobalt. Why? Because skin is not transparent plate glass. It is a scattering medium with depth and color of its own. Shorter wavelengths, blues scatter more near the surface, reds dive deeper before they scatter. When white light enters the skin, the red portions slip farther in and are preferentially absorbed by hemoglobin in the vein below. Much of the blue scatters back from shallower tissue and escapes. You are not seeing the blood's hue. You are seeing skin's filter and geometry perform a trick. Change the thickness of the skin, the concentration of melanin, the distance to the vein, the lighting angle, and the same vein morphs from blue to greenish to not visible at all. If you need a memory to keep this straight, try this. Press a clear glass against your lip where capillaries run close to the surface and look through. The red is inescapable. Or recall the time you caught a drop on a cotton swab. There is no blue phase, just scarlet to rust. The physics that doctors use, clinicians have long turned color into a measurement. The pulse oximeter on a finger, so ubiquitous it is part of the grammar of hospital corridors, shines two beams of light, one in the red, one in the infrared, and listens to what hemoglobin returns. Deoxygenated hemoglobin absorbs more red light than its oxygenated form. Oxygenated hemoglobin absorbs more infrared. With each heartbeat, the arterial blood volume in the finger rises and falls. The device isolates that pulsatile component and computes the proportion of hemoglobin carrying oxygen. It's a simple poetry of algorithms and absorption, Beer-Lambert, written in bedside language. This is the same reason nail polish or motion or cold fingers can fool the device. The measurement is a fragile conversation with light. When carbon monoxide is present, it binds hemoglobin far tighter than oxygen. The hemoglobin, now carrying carbon monoxide, looks deceptively bright red. A person can be dangerously hypoxic and still wear a color that reassures. Devices that use only two wavelengths can be tricked. More sophisticated spectrophotometers listen at additional wavelengths to tell oxygen, carbon monoxide, and methemoglobin apart. Color, again, is consequence. Clinicians also read faces and fingers by eye. Cyanosis, the bluish tinge of lips and nail beds, appears when there is enough deoxygenated hemoglobin to sway the tissue's combined optics toward a dusky cast. It is not blue blood. It is the play of deoxygenated crimson behind skin and mucous membranes. When a baby's lip pinks up after a cry, you are watching oxygen re-enter the sentence. The red cells craft, pause, and marvel at the delivery van doing the painting. A human red blood cell is a flexible disc about 8 micrometers across, so small you could line 100 of them across a hair with room to spare. Its biconcave shape is not an aesthetic flourish. It maximizes surface area to accelerate the diffusion of gases. There is no nucleus to get in the way, no mitochondria burning the oxygen it carries. The cell runs on glycolysis and devotes itself to hauling. Stack 1,000 of these cells to the ceiling of a capillary, squeeze them through a vessel narrower than themselves, and they deform and slide, then spring back, like the silent acrobats they are. Inside, hemoglobin is packed at such concentration that the cytoplasm behaves like a soft crystal, a crowd that increases efficiency without jamming the aisles. The red cell's greatest trick may be its timing. Born in the marrow, matured and released, it will tour your body for about 4 months. The spleen will then test its flexibility and filter out the stiffer elders. Iron is salvaged. The heme ring is opened into biliverdin, green, then bilirubin, yellow, which travels to the liver and eventually colors bile and stool. Your bruise tells that story on fast forward. Red-purple at first, then green, then yellow, the rainbow of cleanup. In the middle of this choreography is a molecule called 2,3-BPG bisphosphoglycerate, which nestles into hemoglobin and nudges its oxygen affinity lower, making it easier to let go in tissues. At altitude, your red cells increase their 2,3-BPG production. The dissociation curve shifts, so oxygen is delivered more readily where it's needed. This change doesn't alter blood's redness to your eye, but it changes the underlying math of the color you would measure with precise instruments. The same hemoglobin molecule, tuned by the presence of 2,3-BPG, whispers, "Take what you need," to muscles hungry for oxygen. Variants on the theme. Fetal hemoglobin, built with gamma chains instead of beta, holds oxygen more tightly. This allows the fetus to steal oxygen across the placenta from the mother's blood. If you could spread a drop thin and watch fetal and adult hemoglobin absorb light, you would find small spectral differences. To your eye, both are red. To life, those subtle shifts are survival. Sickle hemoglobin, a variant where a single amino acid is changed, can polymerize under low oxygen, distorting red cells into crescents that snag and damage vessels. The color in a drop of sickled blood may look ordinary scarlet in a thin smear. The drama is in shape, not hue. Thalassemias, conditions where globin chains are underproduced, change the count and size of red cells and the ease with which breath meets tissue. Anemias, iron deficiency, pernicious, hemolytic, wash a patient's inner world paler and can make a person's skin seem waxen. Polycythemia, the excess of red cells, deepens complexion, a ruddy thickness of color. Dermatologists and hematologists both read the same face and reach for different instruments, but their interpretations map back to the same pigment. Strange colors appear at the edges of medicine. In methemoglobinema, iron is oxidized to the +3 state and does not release oxygen properly. Blood looks chocolate brown. Skin may take on a slate hue. In sulfhemoglobinemia, sulfur binds to hemoglobin, and the pigment turns green. Fairy tale blood that doctors learn to recognize. Carbon monoxide's cherry red has already played traitor in countless tragedies. These exceptions, rare and startling, prove the rule. Under ordinary conditions, human blood is red across the entire spectrum of our lives. Blue blood, for real. And yet blue blood exists, just not ours. In the ocean and marsh, horseshoe crabs and certain mollusks run on hemocyanin, a copper-based oxygen carrier that, when oxygenated, appears blue. It floats free in plasma rather than hiding inside cells. Its oxygen affinity is tuned to colder, slower metabolisms. Octopuses and squids, masters of surprise, flash cerulean within. But even they are pragmatists. Their hemocyanin is adapted to the crushing cold of the deep, and some species produce multiple forms to cope with different temperatures. The world did not vote on a single pigment. It improvised. Marine worms offer green blood with chlorocruorin, kin to hemoglobin, but tweaked. Other invertebrates wield hemerythrin, giving violet shades. Antarctic icefish abandoned hemoglobin altogether in their near-freezing, oxygen-rich homes, widening their vessels and racing their hearts to pump clear plasma. Each lineage solved the oxygen problem with local resources. On land, in warm-blooded mammals with high metabolic demands, the iron in porphyrin solution inside cells scaled better. Red is efficiency wearing a cape. History of a color discovered and named. The discovery of circulation, that blood moves in a loop powered by the heart, was not obvious. Before William Harvey traced the paths in the 17th century, many believed blood simply ebbed and flowed, generated anew in the liver, consumed its tissues. You can almost forgive the mistake. Veins look blue. Arteries are hidden deeper. Capillaries are too fine for unaided eyes. Harvey measured, reasoned, tied ligatures, watched veins swell and valves trap columns of blood, and declared the loop. Oxygen was not yet in his lexicon. A century and a half later, Antoine Lavoisier would name oxygen and show that combustion and respiration rhyme in chemistry. Oxygen combines with matter and heat is released. Breath is a controlled burn. Hemoglobin structure its 4 subunits. Its hemes would reveal itself over generations, with Max Perutz finally solving its 3-dimensional form by X-ray crystallography in the 20th century. To see iron's tiny shift into the plane upon oxygen binding is to understand color mechanistically. When scientists recorded absorption spectra and saw the Soret band humming near the violet and the so-called Q bands in the green-yellow regions, they were drawing the fingerprint of red. A pigment was no longer just paint, it was a map of electron transitions. Forensic flashes. In a dim room, an investigator sprays a fine mist and the scene blooms in a ghostly glow. Luminol, reacting with the peroxidase-like activity of iron in heme, produces chemiluminescence. The blue-white flash is not blood's color, it is blood's catalytic signature. The Kastle-Meyer test drops phenolphthalein and hydrogen peroxide onto a swab. The swab turns pink in the presence of hemoglobin's peroxidase activity. False positives exist. Certain plant peroxidases can mimic the reaction, but in practice, the chemistry is an arrow pointing toward red you cannot see. Forensic science is, in this way, color's shadow language. Culture and metaphor only work because the chemistry is consistent. There is a reason idioms travel so well. Hot-blooded, cold-blooded, bad blood, blood ties, blood on one's hands, blood, sweat, and tears. A painter can choose ultramarine or vermilion. A poet can choose thunder or whisper. A body has fewer options. Its oxygen budget is strict. That strictness gives metaphors a hardness. When we say a story is in our blood, we are leaning on how relentlessly these molecules do their jobs. Our passions feel red because the chemistry does not blink. Mountains shape red. Climb and the world thins. On a Himalayan pass, oxygen's partial pressure falls. Each breath carries fewer molecules. Your body answers in days and weeks. Ventilation increases. The kidneys' sensing systems release erythropoietin, a hormone that nudges the marrow to make more red cells. Over time, your hematocrit, the fraction of blood volume occupied by red cells, rises. The blood thickens. Delivery improves, but at a cost of viscosity. High-altitude populations have found different genetic compromises. Some increase red cells dramatically, others improve ventilation and blood flow without pushing hematocrit as high. Whatever the path, the pigment remains. The point is not to change red to blue, it is to change how much red there is and how tightly it holds oxygen. Athletes, chasing marginal gains, have tried to cheat this budget by injecting erythropoietin or blood doping, transfusing extra red cells. Performance rises. Risks rise with it. Higher viscosity, strain on heart and brain. The color does not tell you who cheated. The numbers do. Color alone is a poor detective. Science needs spectra and counts. 2 small puzzles. First puzzle. If blood is red, why does a large pool of it look nearly black? Because thick layers of pigment swallow almost all light. What escapes is little and often from the blue end after complicated scattering. The surface glare may be white. The bulk is a dark, almost featureless red-black. Thin a smear on glass, and the color returns. Color is not only what you are, it is how much of you light encounters. Second puzzle. Why does the red of arterial blood sometimes look too bright to be real? Because in thin layers under direct light, the long wavelengths that survive are pure enough to seem unreal to a brain accustomed to mixed reflections from textured surfaces. Nature rarely offers pure spectral reds. Blood, in the right geometry, does. A brief tour of color vision. Your retina measures color with 3 kinds of cones tuned roughly to short, medium, and long wavelengths. The long cones are most sensitive not to deep red but to yellow-green. Your perception of red is a computation. The brain compares the outputs of different cones. Place a blood drop against a green leaf, and both colors intensify because the opponent processes in your visual system exaggerate differences. Place it against a red cloth and it may look less striking. Color constancy, the brain's attempt to keep colors stable across different lighting, adds another layer. We are unreliable witnesses to exact wavelengths. We are brilliant witnesses to differences that matter for survival. ABO, RH. And the fact that type doesn't change color. To a transfusion scientist, O, A, B, and AB are not letters but sugar sculptures on the red cell's surface. RH is a protein complex with D antigens and others. These molecules tell the immune system who belongs and who does not. They determine whether a transfusion will sustain or sabotage. They do not tint the blood. Type O and type AB look the same to the naked eye. It is only under the lens of agglutination reactions, antibodies cross-linking cells into visible clumps, that the types reveal themselves. Color remains iron's domain. Why iron and not something else? The geologic part of the answer belongs to deep time. Early oceans were loaded with dissolved iron. Before oxygen rose in the atmosphere, iron drifted in solution. As oxygen increased, it precipitated in bands of ironstone that now ripple through cliffs. Life learned to use iron because it was near and redox flexible. Iron cycles between ferrous and ferric states with ease, offering reversible binding to oxygen if shielded from mischief. Hemoglobin's protein cradle lifts iron's reactivity out of the general soup and confines it to useful work. Copper is also abundant and redox active. Hemocyanin proves it can serve, but copper's chemistry favors different architectures and is less forgiving in the warm-blooded, high-demand niche. Magnesium sits at the heart of chlorophyll. It makes green by sending back a different slice of the spectrum and filters the sun into sugars. Swap the central metal in the porphyrin and you swing the color wheel and the life strategy. The planet is a laboratory, still in session, the choreography at the capillary wall. Imagine the lungs alveolus, a bubble lined with a film thinner than a whisper, rich with oxygen. A red cell parachutes through a pulmonary capillary. Hemoglobin loads oxygen. The color brightens in that delicate film. Now imagine a working muscle. Warmer, more acidic, richer in carbon dioxide, lower in oxygen's partial pressure. Bohr effect, Haldane effect, the presence of 2,3-BPG, all these nudge hemoglobin to set oxygen down. The red dims by a fraction. That gradient brightening in the lung, dimming in the tissue, is so slight your eye will never track it, but your life depends on its precision. A single oxygen molecule is too small to carry good drama. Billions of them flowing second by second make a person. Micro-illusions and macro-truths. A vein looks blue under skin, a pool looks black, a bright drop looks cherry, stale blood looks brown, a bruise runs a rainbow, cyanosis looks blue, methemoglobinemia looks slate, carboxyhemoglobin looks falsely bright. A pulse oximeter reads false in cold hands. These are micro-illusions. the surface froth of a simple macro truth. Human blood is red because iron in heme eats blues and greens. The world's counterexamples, copper blues, green chlorocruorins, violet hemerythrins, clear ice fish are not refutations. They are alternate chapters in the oxygen story, an ambient redemption. Sometimes the quickest path back to appreciation is to hold a number in your mind. At rest, your body uses about a quarter of the oxygen you deliver. During sprint or panic or laughter, you can draw down more. At sleep, less. With each transit through the systemic circuit, the hemoglobin leaves a fraction of what it carried. The exact fraction changes by need, and your chemistry adapts without orders from you. That invisible generosity glows red whether or not you look. You are not the conductor. You are the train, the tracks, and the passenger all at once. The last room, the answer in ordinary light. We have walked through pigments and pulses, mountains and marshes, laboratories and legends. The red has not lost its power by being explained. If anything, it has gained texture. It is tempting to wish for a poetic twist that perhaps blue was hidden somewhere, a secret only sages knew. There is no secret. There is only the luminous fact that a metal chose a ring chose a fold chose a color, and that color chose a species of meaning. You and I are alive in that choice. So here is the clean answer, the one you can say out loud to a child or to your own skeptical heart. Blood is red because its oxygen-carrying protein, hemoglobin, contains heme, a ringed molecule with an iron atom at its center that absorbs blue and green light and allows red wavelengths to reflect and transmit. Oxygen binding subtly changes the shape and electron distribution in heme, brightening the red. Losing oxygen deepens it. Human veins only look blue due to how skin scatters and absorbs light. The blood within is always a shade of red. Other animals can truly have blue, green, or violet blood because they use different metals or molecules to carry oxygen, copper, and hemocyanin, variants of porphyrins or iron without heme. Our lineage, tuned for warm-blooded life on land, found iron in heme inside red cells to be the best solution, and the color followed. And here is the ending you cannot see, but you are living right now. While these words settle, the capillaries in your brain are a constellated city, and across each thin bridge, hemoglobin brightens and dims. A river of small scarlets carries thought. If you could paint your inner life without metaphor, you would pour 1,000,000 shades of red across a black canvas and call it breathing. You would add the faintest blue haze near the lips, only to remind yourself what illusion looks like, then wipe it away. You would lie still and listen to a quiet drum, and in that beat, you would hear the story again. Iron, heme, oxygen, light crimson written in the language of survival. Why is blood red and not blue? Because the universe gave us light with many wavelengths. Because chemistry gave us a pigment that chooses among them. Because evolution gave us bodies that run hot and true by borrowing oxygen and returning it. Because skin and brain are easily tricked, but molecules are not. The color on your fingertip is not a symbol, it is the residue of a solved problem. And yet, like all good residues, it stains everything it touches with meaning.